precede this by telling you a little story. Let's see, can I close this door? So our subject today is going to be fading channels. It is the fourth part of a six-part series. The dates for the others are not established yet. And so the first three parts that we've gone through were all had subjects. And here we basically have one subject that's going to keep us here for quite a while because there's a lot to say about it, fading channel. Let me start by telling you, when I was a very young engineer at the Aerospace Corporation, my office mate was a brilliant young PhD who I was always fearful of. I mean, he knew all the answers. Not only did he know all the answers, but he once told me that the way he likes to see a technical problem is only with equations. He wants to see those parameters dancing around. Doesn't want any words to interfere with that or any pictures to try to enumerate and confuse him. Just the equations is what he wants. And that made me feel very small because I felt that I was at the other end of the spectrum. I needed to see lots of explanatory words and lots of pictures to really understand the application. And we went through life that way. He was brilliant, and I was always stood what I thought of as in his shadow. But I think I have something to contribute by adding a lot of pictures. And what you're going to see today is a picture show. I'm going to show you what is generally assumed to be a pretty complicated subject. The mathematics goes back to the 1950s and 1960s when it was established, and only recently in the 1980s when cell phones started burgeoning did we find that the same mathematics really applies to the challenges that we have in today's wireless communications with that. So remember, the whole idea is not to take away from any of the precision, but to add so many pictures that you're bound to get a feeling for it. So stick with me, and if what I'm saying isn't so, just ask for more pictures. Fading channels, first we'll characterize them, and then we'll try to fix the degrading effects. And so I'm not going to read this whole thing to you, but this is just to give you an idea that it started a long time ago in the 50s and the 60s when we used HF band for over-the-horizon type of communication in the ionosphere propagation, and the UHF and SHF bands were used for tropospheric scatter. And it was in those early days that the idea of multiple paths, hitting various layers of the atmosphere that reflected in a different way and gave you different paths where it was first seen. But when the 1980s came along and mobile communication applications, that's when all of the math that was developed in the 50s and 60s suddenly reemerged as important to us. So our first goal today is to describe the fundamental fading manifestations and the degradation effects that they can bring about, and then we'll talk about methods for mitigating those. So as you can see, just to get a picture of an urban environment where you have a cellular telephone with a base station, say on the top of some building here, and you're riding along one of these avenues. This happens to be New York City. This is 6th Avenue right here, if you know New York City. And you can see that there's got to be more of a challenge than a simple line of sight communications as you're riding in your vehicle and you're trying to communicate with a base station and hand over to other base stations. There's bound to be lots of reflections, multiple paths, and more challenges than just a line of sight. And so this is a little picture I picked up to just show you in a very simple way a free space, and that means the inverse square law as in optics, that the signal in free space A is just a line of sight, it attenuates, and the power attenuates as a function of the distance squared, inverse square law. And so there's also a reflection that just like a mirror, reflections are, we're talking about relatively large items like a big billboard or a big surface, and so it acts just like a mirror. And then let's jump to number D, scattering, because scattering, see this tree-like device, is much like reflections, but it's the dimensions of the surface is closer to a wavelength or smaller than a wavelength, and what you get then is just reflections in multiple directions, and the name given to that is scattering, scattered reflections. And finally, diffraction is probably the most interesting one, because it gives you, it was developed by a fellow by the name of Huygens, a Dutch physicist in the 1600s, and he saw this with optics, of course. There were no radio communications, and he simply saw what appeared to be bending, and we'll show you where that comes from very briefly. I'll show it to you. So when you take a look at the mobile radios experience two types of fading. The large-scale fading is just talking about motion over large areas. The distribution is log normal. That means if you collect the power received in decibels, you'll have a Gaussian distribution. That's what log normal means. And then there's small-scale fading. In the literature, some people call this short-term fading. I hate that name because we have so many types of time that we're going to be looking at. Display time, receive time, delay time. I don't want to add another time. I call this small-scale fading. I prefer this nomenclature. Small changes in position can cause dramatic changes in amplitude, and it results in a kind of a Rayleigh fading distribution, which we'll explain as we move on. So we're not going to have much to say about large-scale fading. This is about it. We're going to say that there is a path loss law, that's like a nth power law. See, if it's line of sight, it's the second power law, the inverse square law as an optics. But so that gives you sort of a mean of where the signal power has attenuated to. And there is statistical variations about the mean, which we have already said is log normal. And something that's about all we're going to say, because our most important interest is the small scale fading. So notice, if you take a look at the envelope, R of t, of a waveform that's propagating through space, and if you let this alpha of t be a dimensionless kind of a multiplier that has two components to it. M of t, you can think of it as the local mean, and R0 of t are the ups and downs of the fading. So this alpha of t looks like this. It's going up and down, and it's also attenuating. So if you integrate like 20 or 40 fades at a time, and solve for this t sub, this m of t value. That's how you solve for m of t at time 1. And as this is a sliding window, as this integrator sort of moves along here, you get m of t1, m of t2, m of t3, and you get m of t, the local mean. If you throw out the local mean, and all you have are the ups and downs, and this is what we're focusing on, as, in my opinion, being the most important characterization of the fading phenomena, small-scale fading. So, and notice that even if there's no apparent movement between a transmitter and the receiver, there can be multi-path changes due to what's happening in between the path. Vehicles, pedestrian traffic, seasonal changes, leaves on the trees, and so forth. So there's a whole history of propagation parameters. We're not going to read them, but to tell you that if you read them at your own time. The final path loss law as a function of distance has three components, 1, 2, and 3. The first one looks like the inverse square law up through the distance d sub 0. What is the distance d sub 0? It's application oriented. So notice that if you're talking about large cells, it's 1 kilometer. If you're talking about microcells, it's 100 meters. If it's indoor, d sub 0 is 1 meter. And this is what is called the nth power law that we talked about in large-scale fading, and this is the variation about that mean. So the whole picture looks like this, 1, 2, and 3. 1 is that for the first distance, d sub 0, there is the same kind of an inverse square law that you would get if you had a line of sight or just figured out how this beam is attenuating. And so it's an nth power law is n equal 2. And then there is the nth power law, which is item number 2, and that could be n equal 3, 4, 5, 6. In general, there's got to be something to start with. You don't know what your environment is exactly. People usually start with the n equal 4th power law until they know better. And then there's the distribution about the mean, which we said is a Gaussian distribution, and that's a log normal with not collected in decibels. Here's an example of making measurements in different parts of the world. These are locations in Germany, Stuttgart, Düsseldorf, a certain bank building, Hamburg, and so forth. And there's an ensemble of various measurements that were made, and notice what they're measuring, and that is path loss between T and R, the separation in kilometers between the transmitter and the receiver. So they have all these points, with diamonds or circles or squares, depending upon where it was taken. And as a result of that, they can simply extrapolate, n equal points that fall around here, fall around an n equal 1 law, around here, and n equal 2 law. And if you take the whole average of this whole ensemble, it looks like an n equal 2.7 law, just to give you an example of some various measurements that we made. So just as we showed you before, you know what we mean by reflection. It occurs when propagation of an electromagnetic wave impinges upon a large surface. And if you drop down to scattering, it's like a reflection, but we're talking about small surfaces. And the interesting one was the diffraction, where it appears to have a bending. Question?
Dr. Sklar, in the previous slide, when you spoke about the PA building, in the figure, the PA building, so in the legend, it says something as a PA building, right?
Oh, yeah.
So for each and every city, that is at different places, and for indoor models,
So he's talking about in the vicinity of this, he's just locating different regions, and it's not, rocket science. He's not making exact measurements of where he was exactly in this building. He's just identifying different, because one area might be suburban, very low buildings, and maybe Dusseldorf might be a much bigger city with larger buildings. So he's just identifying different locales as a generality.
And in the transmitter receiver separation, so was this done for indoor models as well, or only for outdoor models?
Outdoor. These are all outdoor,
Only
not
outdoor.
indoor.
Yeah, outdoor.
Outdoor model.
Only outdoor. Okay, so notice that it was Huygens in Dutch physicists, and basically the fraction is the bending of a wave around objects. I remember the first course I had, Physics 101, you had a razor blade, and you basically, Physics 101, and you basically, shone a light, and you saw the bending. You could actually trace the bending that happened. And what that, and for cellular purposes, it's wonderful, because it says that if you have diffraction, you really build up a secondary wave on the other side of the obstruction. That's what the bending looks like. And it means you can go through what appears to be go through an impenetrable body because it sort of bends around it. And notice it says that this says as telecom goes to higher frequencies of shorter waveforms, the diffraction around large hills lessens. And if it lessens, it means you're going to need more base stations because you're not going to be able to bend to a particular base station. The bending is not going to be as pronounced. Okay, we're going to move quickly because we have a lot to cover. So when you take a look at the big picture, the large scale and the small scale fading, and you say, what do I have to have in the way of margin, safety margin, when it comes to calculating power received in a link? Notice what you need. So you need, for both the large scale fading and the small scale fading, see the large scale fading is purely a Gaussian when the numbers are in dB, and here is this Gaussian expression. And so if this is the base station and this is the mean path loss to the midpoint here, what you really need to have, let's say 98 to 99% of the cases here is this much excess margin. See, this is what the mean would dictate in the way of how the signal power has attenuated. But look, to cover all of these cases down here, you need this much excess margin just for the large scale fading. Now, superimposed on that, the small scale fading is always sitting on top of the large scale fading. And of course, that one is Rayleigh, so you've got a different shape, a Rayleigh shape. And again, another line here says there's another big, large amount. These two together can easily run like 40 decibels, an enormous amount of safety margin that you might have to carry with you if you chose to do it that way. Notice that there are a lot more clever ways to do it than just always have excess power. So, again, that's where the mean would take us, but of course, the mean would take us here, and with the excess margin for the large scale fading, this is where you'd be in the loss of power. This is where you'd be if you had both of them, the worst case scenarios. What are the two fading mechanisms that characterize small scale fading? That's what our focus is on, small scale fading. So here they are. On the right-hand side, you have, let's talk about this one first. There's the time spreading mechanism due to the multitrack. That is, there's echoes. That's what, and this is the time spreading that we're talking about, the echoes. So you can think of it as signal dispersion is the number one mechanism that's happening in small scale fading. And there's the time variant mechanism due to motion. Now, let me emphasize this multiple times. When you think about something that says time variant, you might think to yourself that there is no time stationarity here. Time is varying. Time is varying only because you're moving. So what's really varying is you're moving to a different spatial location. So when you move to another spatial location, suddenly the buildings that are throwing out the echoes of the signals bouncing off are slightly different. If you were standing perfectly still and watching the clock, that's not the time they're talking about, because then everything is perfectly stationary. Nothing is changing if you're standing still. It's only due to motion that we're talking about a change as a function of being spatially located somewhere else, not due to your watching the clock. There is a time change, and it's referred to as the time variant mechanism. Be aware it's all due to the motion. So from this point on, we focus primarily on this more dynamic and interesting small-scale fading. And you can think of the large-scale fading is always present, but it can be thought of as the background local mean that depends upon the kind of terrain. Are you going over agriculture, water, buildings, and so forth? Now, in 1963, it was Phil Bellow, whose name doesn't have the kind of familiarity it deserves. But he's the one who first introduced the idea of what is today, I don't know how you pronounce it, the WSSS model. The WSSS model stands for the Wide Sense Stationary Uncorrelated Scattering Model. And what's beautiful about this is, you see, this model assumes that the channel correlation functions are invariant over time, and that the scatterers with different path delays are uncorrelated, and the WSSS assumption is realistic to describe small-scale variations for, now this is the important time, for all time and all frequencies. So that's what makes it so universally wonderful, is that you can apply it, the statistics that we depend upon is not the first moment, is not the mean. It only depends upon the change in time or the change in frequency. The change is not the first moment. So it can be, with such a model of small-scale fading, Bellow was able to define functions that apply for all time, all frequencies, which makes it so beautiful for us. And here's what these functions are. Yeah, multipath intensity profile, space frequency correlation, space-time correlation, Doppler power spectrum. And I hope by the time you walk out today, you will walk away with a picture of what these things are. Because the person who next picked up on this model, who made these pictures come to life, is Paul Green. Paul Green, who worked at IBM years ago in the 50s, was the co-inventor of the rate receiver in spread spectrum receivers. And you know who picked it up after Paul Green was John Proigis. So here is his reference to Paul Green's. This is the original diagram that you're looking at here, is pictured in this reference. And if you look at every one of Proigis' books, and in fact, you know, when I studied with the Proigis book and got to this page, that's where I found the whole book, to me, found its value in this one page. I walked away from this one page feeling as if I finally had an understanding of what fading channels were all about. And here they are, and this is the way we're going to talk about these pictures, in the way you see these numbers. 1, 2, 3, 4. Multipath spread, and this is the space frequency space frequency correlation function, space time correlation function, and then this one has lots of names. You can call it spectral broadening, Doppler power spectrum, fading bandwidth, fading rate is a good one. And what you also see is that there are some volumes that Proigis plotted of a combination of delta T and delta F, you know, space, time, and space frequency together. And here too, of the Doppler spread and the multipath spread together. But we're not going to look at that. We're going to pay attention to, and notice what I'm calling this. I'm calling this the big picture. This is what you're going to walk away with this afternoon, and that is a good feeling of what this is all about. So the first thing to notice is that, first of all, you're looking at a different mechanism. These are independent mechanisms. These two have nothing to do with one another. They do not depend upon one another. And so the one that you see here is called the multipath spread, or is the signal dispersion. That was item number 1 of the way we characterize small-scale fading. Item number 2 was the spectral dispersion, or the fading rapidity, and that's because of motion, not because of standing still and watching the clock. Nothing changes with the clock, only because we're moving. And notice that the pictures 1 and 2 are Fourier transforms of one another. Multipath spread and the space frequency, and same here. These are Fourier transforms of one another. And when I look at it this way, notice that 2 and 3 are duals of one another. That is, here I have space frequency, and here I have space time. Here I have a power multipath spread, a power signal is spread in delay time, and here I have spectral spread. So when you take a look at Troakis, he also showed us both of these small-scale fading phenomena in one picture. Very simple picture. The first thing to notice is that these pictures are drawn in ideal shapes. You'll never see on an oscilloscope real signal that's propagating along the way this way. You know, it looks more, it's filtered. So notice that what you're looking at is the response to a pulse that happened at a moment in time. But remember, it's not clock watching. It's a moment in time because you're moving. So this pulse is transmitted alpha times later because the vehicle has moved away. Beta times later, again, the vehicle is moving. Or you're just a pedestrian that's moving. But it's a time later. And so the thing that's nice about this picture is to show you that for every one of these four cases, that you get a response that clearly shows echoes, that clearly shows a fading profile. But look, they're different. You know, they're different amplitudes, they're different quantity, numbers of them. There's a different fading profile. And that has to do with the fact that you move to another spatial location. So you're not seeing the same fading profile. So the response to each pulse shows the echoes, multipath spread or fading profile. The response at a later time due to movement or spatial separation is a different fading profile. And the profiles are quite different because the time elapsed between the transmission events, A and B, etc., is greater than, and you can't appreciate that now, but you will later, greater than the coherence time of the channel. Okay, so I'm now introducing something different to you. An idea of boundaries. And look, on one side of the boundary, you see things are bad. And on the other side of the boundary, they're awful. Notice, there's no such thing as a fading giving you something good. Everything here is, the best you can do is to have something bad. That's the best you can do with fading. And now, having said that, let me make one correction. I know there are a lot of you who are interested in MIMO. You know, MIMO, if you got rid of fading completely, would MIMO work? No, it wouldn't. MIMO depends upon a rich assortment of multipath in order to work. So, you know, it isn't really correct to say that fading is always bad or awful. For something like MIMO, it depends upon having a rich assortment of multiple paths. But, you know, just trying to have either a spread spectrum or an OFDM system that can work around this, just to alleviate it, to mitigate it, we can't put ourselves in a starting position and say we're good. We're either bad or we're terrible. So let me, and again, tell you what we've done here. So we've got two types of fading behavior, bad and awful, for each mechanism. And remember, the mechanism is signal dispersion. That's everything on the right column, and spectral dispersion, everything on the left column, viewed in each domain, time and frequency. Time, frequency, Doppler shift in frequency, time. And so, and again, let me number these as we're going to look at them just like we did with the Troakis figure, 1, 2, 3, and 4. And even to make it clearer, let's put those figures right there. This is a multipath spread. And again, what you're going to see is I'm going to dictate, based upon these parameters, T sub m represents a multiple spread that you're going to get as a result of this delayed echo. And when these are related with this kind of an inequality, it's going to result in two kinds of fading, one really bad and the other one awful. And we'll go through all of these pictures to show you the mechanism affects what we're going to get. So this came from a magazine article and a book that I wrote a long time ago, where first of all, I tried to put some organization on the whole idea of fading. You know, that's what engineers like to do. They like to at least start by packaging things. So the only thing I want to tell you is that this is all we have to say about large-scale fading in this here, and that is there's an inverse, nth power law, which gives us the mean, and variations about the mean. That's it. We're finished. Everything else is small-scale fading, and our greatest interest is this everything else, small-scale fading. And again, notice where there are Fourier transforms, and where there are dualities, and again, where you're winding up with frequency selective is a name given for awful fading as compared to flat, which is bad, and that's for the mechanism which is known as signal dispersion, but the mechanism which is known as the time variant nature, because you're moving, again, you got an awful and a bad, and they are named simply fast fading and slow fading, respectively. So let's go back to, where I was here, page number 15, and I said, what does each plot describe? And let's start with the multipath spread, signal dispersion, and let's start reading from 1 here. So the multipath intensity plot shows the signal's received average power, main lobe, and echoes as a function of time delay. So notice this TAW, again, we have to be very careful with how we designate time, means time delay, where 0 means not taking into account any propagation delay. Just the normal line of sight propagation delay would be received here at moment 0. And anything else is an excess delay, and that's what this is, excess time delay beyond the nominal propagation delay for line of sight. So you get the first big bang as think of it as the line of sight, if you like. These are also referred to as fingers of return. And again, there's a kind of an envelope here showing you a kind of an attenuation of the fingers. So it's power received as a function of time delay. And T sub n represents the maximum spread in time that will happen there. A maximum, it's nice to play with it as we're looking at pictures, but it turns out to be not a very good statistic. Neither is the mean. So we'll introduce later on what is called a root mean squared. We'll show you that later. And of course, right above that is the Fourier transform. And the Fourier transform is called the space frequency correlation function. It shows the spectral correlation of received narrowband space signals that are delta f apart. Now, let me tell you what's useful about it. Let me explain how you actually measure this with equipment. Delta f represents the spacing between two transmission tones, f1 and f2. So what you're going to do is you're going to send out a whole bunch of different spacings. That is, you send out an f1 and f2 that's very close together. You individually receive each one of them in some complex receiver with amplitude and phase, and you ask the question, how well are these correlated? And then you do it again. F1 and F2 spaced further apart. F1 and F2 spaced further. You actually send a chirp. You actually send a chirp because the chirp gives you the ability to have all of those spacings in there. And what do you get? You basically get a region in the channel where things are, the received signals, F1 and F2 at certain spacings, are highly correlated to one another. How high is highly? We'll talk about that in just a moment. And outside of that regions, they're acting quite independently. They're not correlated at all. And that's an important region, and we call that F sub 0, and it's called the coherence bandwidth. Why don't we call it the correlation bandwidth? Because that's where things are highly correlated. I don't know, that's what the industry has decided to call it. So it's the coherence bandwidth. And every terrain, every region has a different amount. For instance, take a guess. What do you think if you were in Salt Lake City in some nice urban, suburban area? What do you think the coherence bandwidth would be like in Kansas City or Salt Lake City or some Midwestern small towns? I'd say maybe as high as a few hundred kilohertz. What do you think it'd be in New York City? It's about 40 to 50 kilohertz in New York City. In other words, as you're going to a big urban environment, the spacing is very small before suddenly there's no correlation at all between F1 and F2. Okay, so that's how you'd actually measure the coherence bandwidth, is by actually sending out two tones and doing it again and again and again with a bigger and bigger and bigger separation, and measuring how well at the receiver they were correlated with one another. Okay, what about the fading rapidity? A totally different mechanism, 3 and 4. So notice that 3, space-time correlation, it is the duality of the space-frequency correlation. So notice how you would measure it. You would measure it by sending out a simple narrowband sinusoid at time t1, and then some delta t later, like a time t2, you send out another one. And individually receive them with some complex receiver amplitude and phase, and ask the question, how well are they correlated? Just like we did with the space frequency correlation. And then we'll do it again, T1 and T3, T1 and T4, T1 and T5, T1 and T6, and always asking the same question, how well are they correlated? And again, we get something that has they have a kind of an amorphous shape, because I haven't specified really an exact model. And again, do you see that they are the duals of one another? And you're going to get a region named T sub 0, which is known as the coherence time. And that's, and when you're, notice that when we were talking about this whole area here, we were talking about all of this mechanism is due to the terrain. Are you in New York City or are you in Kansas? Will be the difference of what F sub 0 is. And by the way, approximately F sub 0 and T sub m are the reciprocal of one another. F sub 0 within a multiplicative constant is just 1 over T sub m. And it's only dependent upon the terrain. And when you're looking at this next one, it has nothing to do with the terrain. It has only to do with the velocity. How fast are you moving? And so one of the last things we're going to do today is look at the application on a high-speed train. Well, when you're looking at a high-speed train, as when they were designing GSM in Europe, they want to know what is the coherence time, what region of time on this vehicle that is going 300 kilometers per hour is a reliable one for me. That is when I'm looking at any data within that time, I can do some signal processing in a reliable way at that time. So, and again, you can see that it is equal to the reciprocal of what you see down here, the spectral broadening, which we'll call F sub D. So I'm laying down the sort of foundations, and these, of course, are Fourier transforms. What would each plot look like if there were no multipath at all? And so notice that there were no multipath. What you'd see here is, that is, the channel is the same Monday, Tuesday, Wednesday. Remember what this mechanism on the left-hand side is. This is a function of your movement. So as time goes on, and it's only because you're moving. Everything always looks like the same components if there is no multipath. You know, I call this an equal opportunity channel. See, all of the signal spectral components are going to be treated equally. All of the signal's time components are going to be treated equally. Flat is what the correlation function looks like. And f sub 0 goes to infinity, just like t sub 0 goes to infinity. There are no signal echoes. There is no Doppler spreading if there were no multipath. Okay, let's consider the relationships among those four pictures, and remember the devil is in the details. So again, this is what we're looking at, and we're going to want to look through each one of these four. 1, 2, 3, 4, just like that. And let's start with this one first. And let me show you that the most important, and I think when I describe to you the phenomenon of the worst case fading here, it'll make sense to you. You'll see this in a moment. What you might not see is why the worst case is called frequency selective, when after all we're looking at the time domain. There is no frequency here. Why is frequency selective? Why is it called frequency selective? What does it mean? But you'll see that when I look at the transform world, remember the transform is just another way of looking at it. You're looking at the same phenomenon in time, in the time delay mechanism as you are in the space frequency correlation function. And there you will appreciate the name and I think the mechanism as well. So remember what we're looking at. We're looking at the multipath intensity profile. That was the name given to picture number 1. And here is the worst case. The worst case picture is when, and it's called frequency selective fading, when T sub n, here it is. See, I'm sending out the red signal. You got the main bang, echo, 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 and it's over. So here is T sub n, this duration. Then I send out the blue signal. And then I do the same thing, and it's over here. This is the same value, T sub n. Then I send out the purple signal, it's over here. Then the brown signal. And they all exist for echoes happening over the maximum multipath time delay of T sub n. And when you take a look, at T sub s, the symbol time, let's say this is one symbol, this is the next symbol, and so forth. So therefore, if this is the symbol time, and I send out symbol number 1, and you get all these echoes, but what I have to see is symbol number 2 is arriving exactly at the end of symbol number 1. This is the end of symbol number 1. And here starts symbol number 2 with all its echoes. Here starts symbol number 3 with all its echoes. So by the time you're looking right there, at any point, such as at some toss of A, what have you got? Going into a receiver, going into an ordinary receiver, having a signal within this window of time that you're trying to detect. Do you see the horror of what you've got? You've got the original red, and a piece of the blue, and a piece of the purple, and a piece of all of them interferes with it. Isn't that a horror? And that is the worst case fading, called frequency selective fading. Again, the name isn't obvious because we're in the time domain, but it'll become obvious in a moment. So, and let's take a look at the other side of the coin. What happens if T sub n is over? See, let's say this is a symbol time right here in this picture. Symbol time, symbol time, symbol time. And the T sub n, the multipath intensity profile is finished before the next symbol begins. So there is no smearing. There is no smearing. They're still fading. I mean, it's never good when there's fading because there's lost energy when there's fading. But it's not, it doesn't smear. And if it doesn't smear, it doesn't cause distortion. So this is a case where you have flat fading. And another name for flat fading is frequency non-selective fading. That is, again, something you can't appreciate until we go into the frequency domain. So there's no smearing, and hence there's no intersymbol interference. And now let's take a look at that Fourier transform, which is, remember what this is. This is the space frequency correlation function. And I want to see the same kind of a picture that I did before. I want to compare it to my signal. And that's what I'm doing here. So you remember this is the space frequency correlation function, and we'll call this range right in here was called f sub 0, essentially approximately equal to 1 over the maximum multipath intensity spread. And in this case, this is another example of frequency selective fading. So in what you see here is that whenever f sub 0 is less than, this is the reciprocal of the symbol time, which means the symbol speed, or your signal bandwidth. So remember, this is 1 over t sub s is the same as your signal bandwidth. Whenever you see W, we're talking about nothing in the channel. It's your signal's bandwidth W. And here I've drawn it in green. Now, keep in mind, this is the worst case picture, and what it's saying is that for the spectral lines of your signal that fall anywhere within this highly correlated region, within this coherence bandwidth, things will behave properly. No distortion, no smearing. But outside of this region, the result will be the signals will behave quite independently. And that means that there is going to be distortion, and that is the worst case. And so let me show you that these two are Fourier transforms from one another. And so when you're looking at it in a time delay domain, you're looking at this flora, where you're looking again at any particular moment in time has all of these superimposed pulse copies, echoes. And when you're looking at it in terms of the space frequency correlation function, you're seeing a bandwidth of your signal that exceeds f sub 0, so that the response is quite independent, not highly correlated, hence giving you distortion. And now you can see why the name frequency selective makes sense. It didn't mean much when we were talking about a domain called the time delay domain. But now that we're in frequency, do you see what it means to say that the system is frequency selective? It means that there are only going to be a portion of your spectral lines that are selected that are going to be behaving correctly. And outside of that, they're going to be behaving quite independently, and hence intersymbol interference. So again, that name makes sense. And now let's also look at that coherence bandwidth, but this time with regard to a much smaller bandwidth signal. Your signal falls well within that coherence bandwidth. And when it falls well within that bandwidth, that's the case where f sub 0 is greater than the signaling speed or the bandwidth. Remember, this is bandwidth, this is bandwidth. And that means that every one of the spectral lines are going to be treated in the same manner. And when I say same manner, I typically mean in most cases they're either fading or they're not fading, or somewhere in between, but a similar manner. And so there's nothing that falls outside of here that we're saying happens independently. So this is frequency non-selective fading, and that's the name given to flat fading when it's non-selective. And so flat fading is bad because simply fading is bad. The moment there's no distortion, it's not horrible. See, if it's just bad, it means more EBNO can always take care of it. More power can always bring it, a scaling can bring it back up again. But if it's been distorted, you know, it's more than a scaling. It's got to be equalized in some manner. Again, these two make a transform pair. That is the multipath intensity profile that had the picture of T sub n being smaller than T sub s, and it corresponds in the Fourier transform map where the f sub 0 is greater than the lambda. Okay, now remember when I use the words, as long as it falls within here, this is the region where things are highly correlated. Well, and we said, how highly does highly mean? Well, there's been quite a lot of disputes about that. And there are two main researchers who have come in to answer that question. In time, the first one, in 1989, was W.C.Y. Lee, a very well-known researcher in mobile communications, and he dictated a very rigid kind of a correlation. That is, we call that 90% correlated, and that is that this is the approximation we've been using where T sub n is the max. So I haven't yet defined to you how you get an RMS, but just put it on a hold for now. When you get the RMS, and you know it's something less than the max. It's 1/50 times that RMS, and that's going to make for a relatively small f sub 0. But one that's less rigid, we call it 50% correlated, is a wider region by Rappaport, and I think this is the one that's pretty much used in the industry today. Approximately 1/5 times the RMS of the expert. Now remember, this is not rocket science. This is just to give you a sense. As you're watching, I was in a company in Germany, as I was watching them simulate, and they were printing these things out, and I said, oh, let me have copies of these, and you'll see a few other copies like this in here. And I annotated them with, remember what f sub 0 is? F sub 0 is the quantum chunk of what's either pretty good or fading, pretty good or fading. And so, again, you can see how hard it is in a plot like this to put precise values on something like f sub 0. Is, you know, and that's why, you know, just having approximations this broad, you can see, came about because it doesn't lend itself for a lot of it doesn't. It doesn't lend itself for a lot of precision when you're looking at an oscilloscope plot of some speech. This is in the speech range of frequencies. This is from 0 to 5 kilohertz. Somebody was simulating this on a fading channel. And again, I'll show you more plots like this, so you can see that you'd be hard-pressed to get very precise about what exactly it is that's. So now we're looking at this fading rapidity. Remember, this is a totally different mechanism compared to the multipath spread. And we're looking at the dual picture of the spaced time correlation function. So we're talking about correlation functions. And remember, this is the magnitude of the correlation function as a function of that delta t. We showed you how you're going to measure it. And there, too, we can come up with a worst case and best case, and being on a boundary of which side of the boundary are you on. So we're talking about fast fading, and fast fading can be devastating. So in this case, what you have is a symbol time, and the coherence time is something much smaller than, that means that just imagine you're on a high-speed train, and this is the band, and this is the time of the symbol that's coming along. So only some of the time copies, or the time region of your signal is going to be coming through unscathed, if you will, highly correlated in time. And outside of this, they're going to be in a fade, out of a fade, in a fade, out of a fade. It's going to be quite mutilated going out. So fast fading, you may not even have an opportunity to easily sync up on a system that's doing fast fading, because of the size of your pulse is so much larger than what is a reliable. Think of the coherence time of the channel as a reliable region in this moving adventure that you're on. And another way of saying this is that the symbol rate is less than the fading rate. So you're changing symbols relatively slowly. You've got long symbols, and the fading is just chopping that symbol up. Okay? So you can think of it as a mutilation in fast fading. And slow fading, nothing gets good, but it's not awful. It's merely bad. That is, there is no mutilation. The whole time symbol falls within the highly correlated part of the space-time correlation. That the symbol or rate is greater than the fading rate. And so that means that the state's change of the channel can take a long time. And you've got many symbols going in that long time. And those many symbols, well, what is the state of the channel? It can be terrific. It can be good, so you don't see anything bad. Or it can be faded, so you might see hundreds of symbols. So no mutilation, but you got to have an equalizer, because not an equalizer. You got to have an interleaver, so that you never get to see 100 bad symbols. That's a wipeout. But if you have an interleaver, that takes care of it. But there is no distortion again, no mutilation, no distortion. And finally, the Fourier transform of that space time correlation function is what gives us the Doppler power spectrum. And this is the one that there's probably more to be said about this than any of the others. And in fact, of all four of these, I think students have been readily acceptance of 1, 2, and 3 and understanding them rather quickly. But when the Doppler power spectrum comes up, invariably I get questions about how does fading cause spectral spreading of a received signal. So I'm saying that in a fading channel, you can get a spectral spreading of your signal. And to give you that understanding, I came up with an analogy to think of on-off keying of a digital signal, and that's how you can think of how it happens with a fading channel as well. And here's my analogy. Analogy between spectral broadening in fading and spectral broadening in keying a digital signal. So here's a sinusoid, and dot, 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 dot means a forever ongoing sinusoid. Has a spectrum which is a pair of delta functions, one at FC, one at minus f sub c. And notice I start to say, let's key it. Key it says in the time domain, I'm going to be multiplying it by a rectangle so that none of this on the left comes out, none of it on the right comes out, only this piece right there comes out. This is what comes out as a result of this multiplication. Well, when I look at the spectrum of a rectangle, I got a sinc function. And so notice what I'm going to do to see how do I, in the time domain, I see my waveform that comes out by multiplying the rectangle basically a keying is a switch. This is the switching function times the ongoing sinusoid. And of course, in the frequency domain, I'm not going to multiply. What am I going to do? Where I multiply in one domain, I do what in the other domain? I convolve. So I convolve this sync function with these impulses, and there you have what comes out as a result of keying. This is the spectral picture of keyed sinusoid. But now let's say let's do faster keying. A faster keying says, turn that switch on and off faster. It's like saying multiply by a narrower rectangle, and this is what comes out. And again, I do multiplication here, and of course, if I got a narrower rectangle, its spectral, its Fourier transform is a wider spectrum. And if I now, again, take this wider spectrum and again convolve with those impulses, lo and behold, you see that with modest keying, this is what came out. With faster keying, what came out was a broader spectrum. There was spectral broadening. So think of the channel's fading rapidity as the actions of some omnipotent being whose dictates go into a fade, come out of a fade, either occur like the keying in B, slowly, rather slowly, or occur like the keying in part D, much faster. So again, just think that when you're in a fading environment, there's like an all-powerful says in and out of fade faster, keying it faster, and there's going to be much more spectral broadening on the results of your signal, and there is what we mean by the power spectrum, also called the fading bandwidth, if you like. Okay. So, now everything that I've showed you about these four pictures was the Proakis pictures. It turns out that in the wireless community, there is a particular model known as a dense scatterer environment, which dictates, and what really, these don't change, but it's these. This becomes a Bessel function, and this becomes this kind of a washball effect, different than the Proakis picture. So, using the dense scatterer channel model gives rise to these shapes, and I'll just point you to it, and that is that here's what the uniform scattering environment is. Scattering model was introduced by Clark and by Jakes, and in this model, the channel consists of many scatterers round in a circle like this, densely packed with respect to the angle, and we assume n multipath components with an angle of arrival, and the automobile, is like driving in this environment this way. And we won't dwell on it, but when the space-time correlation function takes on this Bessel function, and the Doppler power spectrum takes on this washball effect. So I'll give you all of the mathematics that goes behind it. So I'm using the pictures here, but again, to understand where they came from, I've given you the references. So if you take a look at the fast fading and spectral broadening, notice this is an example of, and that is when the fading, remember another name for this is fading bandwidth. And when the fading bandwidth is much greater than the signal bandwidth, again, what that means is that you're going in and out of phase faster than you are changing your symbol. And that's mutilation and distortion. And they are, that is a Fourier transform with a space-time correlation function, which manifested fast fading. And similarly, when you take a look at the bandwidth of your signal changing faster and the fading relatively slow compared to the bandwidth of your signal, there may be many symbols that go out at a time, but there is no mutilation, there is no nonlinearities brought about that require more work, and this is the Fourier transform pair for the slow fading picture. So again, to sort of summarize the dual functions, here you have a coherence bandwidth, which is telling you, spectrally speaking, does it look like I'm in New York City, or does it look like I'm in Kansas? Or does it look like I'm in a desert, you know? And coherence time is a function of, do I have a few milliseconds like I would on a high-speed train, or would I have hundreds of milliseconds like if I'm a pedestrian walking? So again, those characterize the channel. And notice here the dual functions are, you see signal spreading as a function of delay time, and you see spectral spreading. And by the way, this is a frequency term, nu. The Greek letter nu is used throughout here in the Doppler spread. Okay, now in mobile channels, how does the terrain affect fading, and how does the mobile velocity? Well, this is just a review. We said that already. Remember, everything on this right-hand side has nothing to do with movement. It just has to do with a function of the environment, the terrain. And everything here is a function of velocity. It's called time changes. It might just as well have said spatial changes. So we desire that all fading effects be flat and slow. That's like a going-in position. Whenever we are in a case where we have any kind of a distortion, we are not ready for diversity. We are not ready for taking more copies of the signal, because they may be distorted copies of the signal. Our starting position is we're not ready for anything like diversity or really mitigating it until we make the first step of getting, modifying whatever worst case we may be at, fast fading or frequency selective fading, at least make the change to bring us into slow fading and flat fading. So again, we showed you these pictures, and so I'm telling you that these boundaries and conditions, and knowing what we want, we desire that all fading effects be flat and slow. And so this is what I want here. I want it to be merely bad, not awful. This is what I want here, merely bad, not awful. And that's the makings of a wish list. That's the makings of getting a wish list started. Again, I showed you what zeros look like. And so here's an example of, say, plotting on a plane. I sometimes refer to this as the metaphoric black cloud over us when we're dealing with a fading channel. You know, it's never good. So, in a sense, what is being plotted here is frequency and time, and this is f sub 0. And again, remember, it's not a rocket science, but this general distance here in frequency dictates an f sub 0, or this null in frequency, another f sub 0. So either the ups or the downs dictate just a quantum chunk. And the same thing here with t sub 0. And so I'm going to go through these pretty quickly. I've thrown in an automobile here. Notice that t sub 0 is inversely proportional to velocity, so that as these numbers are getting larger here, t sub 0 velocity is decreasing as this automobile is moving. And so in this particular case, you know, I have some numbers, and the numbers basically look like this is a pedestrian just walking, and pedestrian velocity and multipath spreading in a rural setting with the f sub 0. You know, it could be, you know, some Midwestern town. That looks like 385 kilohertz sounds right for the coherence bandwidth of a Midwestern town. And again, 27 milliseconds is the well, it's not in the hundreds of milliseconds, but it's somebody's walking at 4 kilometers per hour. Well, it's a pretty brisk walk, isn't it, 4 kilometers per hour? That's not just casually walking.
Still fast.
Huh?
Still fast.
Still fast. So, yeah. But maybe it's a bicycle ride at 4 kilometers per hour. Okay. Now, non-mobile correlation functions. So, so I'm looking at, you have multipath, but you're not moving. You're not moving at all. So remember, earlier we showed the y-axis stationary uncorrelated scatter functions, let me misspell this, for an AWGN channel without any multipath. Here we do have multipath, but there is no movement. So notice, if there's no movement, you can still be in a lousy condition of having a multipath spread. There might be buildings all around you. You're absolutely still. You're not moving. There's terrible echoes around you, and there's a small coherence bandwidth. But look at over here. Over here, if you're not moving, you're going to see the same thing Monday, Tuesday, Wednesday as you do Thursday, Friday, Saturday, and there's going to be no spectral spreading. And typically you might see, if you made it kind of a plot that you had before with that black cloud would be, no change. You see a T sub 0 goes to infinity. The coherence time is very, very long. Let me look at it, give you an idea. This will just give you an idea of what Motorola has done in sort of plotting pictures in the Schaumburg, Illinois area and relating them to actual. See, what they do is they make these measurements, and then they look at these surroundings, and they identify with the water tower, this building, and this building, and this building, and they account for what they're analytically seeing in responses based upon that. Now, for a mobile fading channel, remember I said that signal dispersion, everything you see on the right-hand column, is independent of fading rapidity. They are not related at all. And so let's talk about that. In a multipath channel, the same waveform received by 2 antennas that are displaced by about a half a wavelength are statistically uncorrelated. Signal dispersion depends only on the terrain. Fading rapidity depends only on the speed of movement. And for that reason, one can come up with these volume plots, and that's really what Proakis did when he plotted things like frequency and time. So in this particular example, notice the time spread here is 7/10 of a microsecond, simply because the resolution, the time resolution is 1/10 of a microsecond, and you can count 7 of these spaces, so that's 7/10 of a microsecond. And the Doppler spread is like the 3 dB bandwidth of the, typically the largest of these is taken as a measure of that bandwidth. And that volume is sort of giving you the channel gain versus those dual functions. But I think it's interesting for those of you who are looking in the real world about getting things like certificates and jobs and such. There is an organization called the IEEE Honors Communications Engineering Technology, which puts out a certificate. And in order to get their certificate, you have to pass an exam. And so in this last year's exam, I just picked out some little exam problems that relate to fading channels, because certainly in a wireless environment, that's an important area. So notice that a mobile tunnel, by the way, notice that there are going to be some, and this is a trick they do all the time, they give you more parameters than you need. You've got to figure out which ones are you going to ignore. Isn't that a terrible trick to do to a student? I mean, a student goes in there figuring he's got everything nailed down and he knows his formulas. So Student's life is a difficult life. A mobile terminal moving at a speed, a velocity of 30 meters per second is receiving a signal with a center carrier of f sub c equal 2 gigahertz, having a bandwidth of 5 megahertz. The received signal has an RMS delay spread of 2 microseconds, and that's just a better statistic than using a mean or a max. And the full Doppler spread of the received signal is approximately, and that's what you're going to figure out here. So here's the solution. The Doppler spread is velocity divided by lambda. Lambda is nothing more than the speed of light divided by this center frequency. Or, because it's in the denominator, this is the speed of light, this is the center frequency, it's reversed. So you plug in the numbers you're given. Velocity is 30 meters per second. The center carrier is 2 gigahertz. Here's the 2 gigahertz. The speed of light is 3 times 10 to the 8 meters per second. And this would be a one-sided f sub d of 200 hertz. So the answer would be double it. And number 3 is the correct answer. So notice here, the tricky part of this example is recognizing which of the given parameters have no influence at all on the Doppler spread. Remember, that's why we keep these two mechanisms in two separate columns. The spread is on the right. The signal spread is on the right. The Doppler spread is on the left. So things on the left have to do with the these are the parameters: the velocity and the wavelength, the speed of light and center frequencies. So notice which had nothing to do with this problem is the signal law of 2 microseconds, and the bandwidth of 5 megahertz had nothing whatsoever to do with it. So if you made a mistake of trying to use that in your answer, that would really louse you up. But what added information can we foretell about this example by using the additional information? The bandwidth of the signal is 5 megahertz and the delay spread is 2 microseconds. And that is, you can tell the coherence bandwidth. Let's use Rappaport's approximation. Here is the sigma sub tau, the 2 microseconds. And the coherence bandwidth is 100 kilohertz. Not as busy as New York City, but it's an urban environment. And the signal bandwidth is 5 megahertz. And since 5 megahertz is larger than f sub 0, the signaling will definitely exhibit very, very pronounced frequency selective fading. Okay, I said all these things, so I'm just going to leave this for you to read at when you look at it. And this too is a summary that we've talked about. Okay, now remember when I said that this is not a rocket science? I got that way by just looking at this spew of photos that was being printed out in the simulation that I told you was being done in Stuttgart, I think this was, in Germany. And so the speech spectrum used in the simulation was like from 300 to 3,300 or 3,400 hertz was the spectrum. And this is what you see as you walk along. You see the changes. Look, here, there doesn't seem to be very much change at all. When I say it's not rocket science, I mean, you take a photograph of what's happening, it's a random walk that happens there. So you got to take an ensemble of lots of these in order to really dictate, what is the proper value for the f sub 0 chunks, either fading or not fading chunk quantized. And one picture alone, as you're looking at hundreds of them, isn't going to do it. They all change a lot. So you essentially have to come to the conclusion that would have to take an ensemble average over a period of time, and then not rocket science. Now here's an example of looking at a multipath spread with a spread spectrum, direct sequence spread spectrum filter, where notice what we're doing is we're looking at f sub 0, which is of course the coherence bandwidth, multiplied by the time of the chip. And remember, the time of the chip is reciprocal of the spread spectrum bandwidth. So you can also write this as f sub 0 divided by the chipping rate or the spread spectrum bandwidth. And that is like, you know what you want. If this is the coherence bandwidth f sub 0 in here, what you want is you would like W to be well within here, or at worst case, you know, at worst case, you know, W should not exceed f sub 0. So the picture, the first slide shows you here that when f sub 0, and you can, every time you see this, you can replace it by this ratio, and the ratio of f sub 0 to the spread spectrum bandwidth is 1. That's like a borderline frequency selective fading. You're just on the borderline because if the bandwidth, if your bandwidth was any larger, and here's a case where the f sub 0 over the spread spectrum bandwidth is simply a quarter, and that's moderate frequency selective fading, and you see you've got a lot more fingers. The time, as time is going on, is going along that diagonal. And here's the case where f sub 0 over the spread spectrum bandwidth is simply 1/10. And again, you know, that means that the bandwidth is very large, but the coherence bandwidth is only 1/10 of that, and you got like 10 fingers of return. Okay, let's talk about the performance. The good, the bad, and the ugly. Well, the good, we mean AWGN. And the Rayleigh limit for slow fading, flat fading, and I'm going to show you why it is this inverse straight line. And that's the bad. And when it gets worse than that, you know, and it can approach as horrible as probability of bit error being 1/2, you know, that's the ugly. So here's an example just to take a look at what this looks like when it comes to something like text. This is AWGN channel, or what the type we're used to looking at, where you see maybe one bad bit in, you know, you can count it out yourself. There aren't any bad bits here, but, you know, 1 in 10 to the 5, 1 in 100,000. And here, what you see is a slow fading example where there are outages for a while, and yet you can make some sense of it, of what the text is saying. But when you have a fast fading channel, notice you lose it completely. You can't make any sense of it because it's sort of all gone. And typically when multipath causes changes in the receiving amplitude, it affects the phase as well. And I think you can probably see here that when you take a look at those phase errors happening, at the moment you start losing lock, you see there are 3 stable locks here. Around 0 phase error, around plus or minus pi radian phase error. So these 3, 0, plus pi, minus pi, is a stable lock. And anytime it loses lock, and it might come back to one of those positions, you know, so each time lock is lost, the data are inverted and the word error rate increases to union until the loop regains lock. Now, it turns out that the system can resolve itself here by differential decoding operation at the receiver. But you don't want it to lose lock too many times because that makes for word errors that you see here. You know, associated with every one of these little glitches, like the change of its position, is a word error starts out here. Change here, the word error starts in. This little bit here is a word error here. This corresponds to this word error, this one, this word error, and so forth. And the example of in fast fading, what happens is that you're constantly losing lock. and you're trying to recapture it. And that's why in fast fading, the probability of bit error so quickly can degrade to just 1/2, which is, awful. So, and this just tells you that whenever you have a reflected signal, you can think of a desired and a reflected, and a resultant signal, it tells you there is some amplitude loss, and you can always talk about the envelope of the waveform as whatever these components are, whatever this resultant signal is, it can always be broken up into X and Y resultant components, and the distribution if these X and Y components are Gaussian, then the envelope of the signal is going to be the X resultant squared plus the Y resultant squared square root of, and that is typically referred to as a Rayleigh distribution of the signal. And the key difference between Ricean and Rayleigh is Rayleigh is the worst case. It doesn't have any line of sight component here. But with Rayleigh, with Ricean fading, here this Bessel function times this line of sight component makes, I don't want to dwell on mathematics, but what it's telling you is that the Rayleigh goes from 0 and blooms out and blooms back down to 0. And while in the case of a Ricean, as this phasor is going round and round and round, there is a line of sight and there's a blooming on the tip of that vector. So the received low-pass signal in one signaling interval simply looks like this. And for slow fading, we assume that the phase shift can be estimated from the received signal without any error. And for classical AWG channel, we have some fixed attenuation alpha, and then we modify our classical expressions by putting an alpha squared here. Alpha squared is typically chi-squared distributed. For the classical case, you just replace this with unity, and notice what happens whenever, and all this is saying EV over N0 times the expected value of alpha squared should be much larger than 1. But all that means is for any significant amount of EV over N0 above 0 dB, this is what every one of those classical modulation types look like. They all look like a probability of error being of the form K over EP over N0. And that form, that probability of error form, which is EP over N0, is just this inverse straight line. And as EV over N0 goes up, it just goes down linearly. It goes down like a straight line, every one of them. And so when you turn the page, and then you again see, with the exception of these little curvature here, so that's what it means when it says for this expression to be much greater than 1, it just means with this exception here, this is all much greater than 1 here. We've got straight lines for all of these classical modulation types if you have flat or slow fading. Those are the slow fading ones. So starting with a wish list to preclude frequency select, that's what the wish list is going to do. Remember, we said we wish to begin by having flat fading and slow fading. And then we'll take it from there, and we showed you that. And so our wish list relates signaling speed or signal rate or bandwidth to the channel coherence bandwidth and the channel fading rate, so as to preclude the need for equalizers and interleavers. That's just a going in position. Here is our wish list. So f sub 0 the coherence bandwidth, should be greater than the signaling speed, which should be greater than, call this the fading, the reciprocal of the coherence time is f sub d, which is the fading rate. So I put this down. And so this is to preclude, this inequality is to preclude frequency selective fading, and this inequality says this makes sure that you're going faster than the fading rate to preclude fast fading. So again, if you also want to annotate what this number means, this is the fastest that you can go with this arrangement, and this is the slowest that you can go. So you probably didn't realize, you probably had good intuition that in a fading channel, you must not go too fast. And f sub 0 gives you the upper speed if you did nothing else but use it that way. But you didn't know, did you? I'm sure. There's nothing intuitive about knowing that in a fading channel, you also have a minimum signaling rate. That is the slowest rate that you should be going at. Maximum multipath spread, and this is basically the coherence time is the slowest rate. Okay, so this says you probably didn't realize that, but it's true. And again, everything is relative. Fast and slow are relative terms. An average fading rate of 1,000 fades per second would represent slow fading for a simple rate of 10,000 symbols per second, but it's a more serious fast fading for 100 symbols per second. And by the way, that reminds me of an anecdote to tell you about where fast fading was just observed. Fast fading was first observed in the 1950s, 60s, when they were doing tropospheric scatter, and they were sending 75 bits per second teletype. So what they basically saw is that fading rate wasn't very fast, but it's all relative. With 75 baud, it didn't take much of a fading rate to mutilate that 70, each one of those symbols. So that's where they first noticed fast fading. So let's say we start with the wish list, but we invert this inequality and say that suppose the fading rate becomes faster than the signaling rate. So what is the mitigation? Well, choose a modulation-demodulation technique that's most robust in fast fading in order to minimize. That happens to be something like Emory FSK is a good choice for that. Incorporate sufficient redundancy. You know, make this go faster, make it go faster. Put in redundancy somehow, like, you know, error correction coding. That's not really, well, yeah, that's a time to do it. And as long as the transmission symbol rate does not exceed the coherence bandwidth, no frequency selective mitigation is needed. And we should be operating, once you change that by making this go faster, you should be operating at the slow fading rated limit. And then you can do all the other things about that mitigation also. Now, what if this is the inverted? If this one's okay, but this one is inverted, and that says, okay, since this is okay, there's no fast fading problem, but frequency selective mitigation is called for. Consider one or more of the following: partition the data among multiple carriers to reduce. And what is this technique called when we partition the data and put it on multiple carriers or subcarriers? That's OFDM. So that's going to be a mitigation technique: adaptive equalization and spread spectrum. Either frequency hopping or direct sequence spread spectrum. And finally, what if this is the case? What if both of these inequalities are flipped? Notice if both of these inequalities are flipped, then for all practical purposes, you have f sub 0 is less than the fading rate. So remember what this means. This is a difficult design problem because this represents the fastest that you can go. The fastest that you can go is in this channel less than the slowest you can go. That's a difficult design problem. But we can do it. We can fix it. We just take it one at a time. And, you know, we'll just take, we'll fix the right-hand side first. We look at it this way, we'll fix the right-hand side first. We'll initially take a robust modulation, make this, force this one to go faster, and then use some kind of an OFDM for spectrum. So we just take it slowly. Okay, I'll let you look at some of these things on your own. I'm going to skip a few things. Okay. So on page 88, so this is, remember we said that our wish list is not the end all, but it's a good starting point. It's a good way to get started. So the general picture, if you find yourself at a frequency selective or fast fading situation, you can think of mitigation happening in two steps. Step number one is observance of the wish list. That do whatever is necessary to bring yourself down to this inverse linear probability bit error curves. And by the way, whenever we're in a MIMO situation, that's a given. Now we put ourselves in that situation to make sure we have, a rich MIMO, a rich multipath environment, but one in which we have flat and slow fading. We certainly don't want frequency selective or fast fading. So we want these inverse linear probability bit errors as they're going into position. And then mitigation step number two was now we start using diversity. And diversity says, take independent copies, looks at the various signals, which is going to move us in the direction towards an AWGM response. Or from the awful, we go to the bad, and from bad to the good. So let me repeat, I said this, but let me repeat it. Complying with the wish list doesn't by itself provide good performance, but it's a start. It does guarantee not having awful performance. Okay, the wish list is just the start, and now we're ready for diversity techniques. And so we'll go 1, 2, 3, 4, and to combat, first of all, we'll start with the right-hand side of the wish list. That if we are in a fast-fading situation, it calls for robust modulation, signal redundancy to increase signaling rate, coding and interleaving. And if we've taken care of the fast-fading problem, and we might have caused frequency selective fading just by introducing all this redundancy, might make the speed of the signaling faster than the coherence method. So this might have been there originally, or we might have caused it from here. So we are going to either have some adaptive equalization or spread spectrum. And either one of these two techniques, direct sequence or frequency hopping, will work. The popular one these days is OFDM, and that's what we're going to be talking about next time we meet. And a pilot signal is sometimes used. And once we've done that, we've finished with the wish list, and we're ready for diversity. And this is what diversity does. Diversity combats a loss in average signal to noise ratio. So there's lots of kinds of diversity. There's time, like interleaving, frequency, bandwidth expansion, spread spectrum, frequency hopping or direct sequence, and we'll look at that very important rate receiver, space receiver antennas, polarization, and so forth. Okay. This is just to show you that if L represents an independent, let's see, if little p is a probability that any one signal will fade below some critical value, then p to the L power is the probability that all 11 independent fading replicas. So independent is an important word here, because you don't want these additional copies or looks at the signal to be highly correlated to something that might have been crappy before. So at least if they're all independent looks, you got a good chance that some of them are going to be good, better than others, and you're going to wind up with a better performance. And so this is the general appearance of what these inverse linear probability of their curves look like. As you increase L, one look, one copy of each signal, 2 independent looks, 4 independent looks, and you see that you're moving in a direction of a WGN shape of the performance. So again, you can get frequency diversity, time diversity, spatial bandwidth expansion, spread spectrum, coding and interleaving, and there's all sorts of ways of combining signals that I don't want to take the time, but I've given you lots of examples to look at that are worth looking at. But I will, at this point, we only have about 20 pages to go. We're almost done, so we've made good timing. And the 2 things I want to show you that are important are the rate receiver and an example of a wireless system on a high-speed train. So consider a link with one direct path and one delayed path. And that's one, it looks like this. Here's the direct path, and here's the multipath. So obviously, the way I've drawn it, the multipath comes at some tau delay time later than the direct path. And when you take a look at the received signal, here is the direct path. There's the baseband signal, x of t, multiplied by some gain factor, and the PN code, g of t, and the carry wave, cosine omega 0 t. And here is the multiple path, the multipath. That is a delayed version. So here is x of t minus tau, delayed by tau. Same ax here, and multiplied by some alpha attenuation factor, depending upon the characteristic of that particular multipath. And then the g of t, I mean, that's like part of the baseband. So it's that's been delayed, g of t minus tau. And then, again, the carrier wave is affected. So it's a phase delay, as you see here, and there's noise. And you think that this is the delayed finger, and you take that and you put it into the receiver. What does the receiver do? It takes this whole mess and it multiplies. What does a spread spectrum receiver do? The first step in the spread spectrum receiver, what does it do? It multiplies by and perfectly synchronized with the PN code that is that all the participants know about. So I multiplied by the code. So g of t becomes g squared, and g of t minus tau becomes g of t minus tau times g of t. And so the delay, so what you get is this part we refer to as the delayed finger. And in the match filter, when you've done this, look at what happens as you integrate this now. The delayed fingers are transparent because, you know, g squared of t equals 1. And for the case where the delay time is greater than one of those PN code elements or chips, notice what we're doing. We're product integrating gt times g of t minus tau. And as long as this tau is greater than a chip time, see, what is it when you learned about spread spectrum? And what did you learn about the correlation if you take PN code with itself and you just offset it by one chip time? What do you got? You got zip. Well, there are the trivial cases where you won't have exactly zip if the PN code is like 6 bits long for some trivial code. So for any, let's parenthesis long for PN code. Integration over symbol time t of a PN code times itself delayed greater than the chip time will approximately equal 0 because the long PN code is uncorrelated with the one chip offset of itself. So with that giving you zip, what you see that you get here, proper despreading yields the original baseband signal, and noise. Okay. Direct earliest return and delayed return. So when you're taking a look at these as phasors, let me tell you a little bit about the history of spread spectrum. You know that actually this work was done by Paul Green, who was going for his PhD at MIT, MIT, and the big disappointment was that the receiver locked on to the direct path, one finger, and you know whenever there was a multipath, and it locked onto this one path, and all these other fingers were transparent, were not seen. Basically, the code not locking onto it, it didn't come in there as energy associated with that signal. It was locked. And Paul Green and his co-inventor Bob Price said, and the big disappointment in spread spectrum systems is it worked, but it required a very large amount of EB over N0. It wasn't working at the way they thought it would work with a small EB over N0. And Paul Green said, you know, the energy in this finger, that belongs to my chip. I don't want to lose it. That belongs to this chip. This belongs to this chip. That's lost energy, all those other fingers. I want it back. That was the motivation for the rate receiver. I want that energy back. It belongs to me. All those other fingers, and you saw in one example we had like 6 fingers. So let's just go on and skip some things and go right to the rate receiver. So what you see here is a little diagram that sort of says, imagine a PM sequence 10111. That's and every time this 1 is sent out, in this case, it's sent out with echoes. So what you have along the diagonal is transmission time, and so the first one goes out, and multipath arrival number 1. The second sequence goes out, arrival 2. And notice that each pulse, and I've just drawn all the pulses positive so that the diagram doesn't get too busy, but remember, some are positive, some are negative, and each pulse has echoes. And in this case, I've just shown you 2 echoes for each one. You know, this pulse has 2 echoes, this pulse has 2 echoes, and so on. And if you put a point through here, again, the confusion is that, you know, it is, all these things appear as in one symbol, but of course the system will still work. It'll lock onto the code, but it'll require a much greater EB over N0. So this was the idea for the rate receiver. The rate receiver says, I'm going to treat each one of these diagonal lines with a separate receiver, a separate correlator, its own correlator. It's like saying, you know, I'm going to treat each one of these fingers as if I got to have a correlator ready to make a decision on that particular, the second finger, on the third finger, on the fourth finger, because, and the reason why I have to do it with separate ones is because I can draw that faster. The reason why is because you saw that when I had just the 2 fingers and I tried to show them with phasors, one was a phasor like this and the other one was a phasor like this, and I couldn't add those phasors together. I basically had to line them up before I could get them together, just line them up in some way, and then I could add them together. So the idea of a rate receiver was to deal with each of the phasors of the fingers separately and then make a correction. So by the way, in 1958, when this was invented at the and MIT, and Lincoln Labs. They had 30 fingers of return. They had 10 shells with 3 delay lines on each one, making for 30 receiver correlators. And today, a 4-finger rate receiver is used in most every cell phone, which is just a little portion of the chip actually. And this is what the first rate receiver looked like. And again, the whole idea was the motivation was to retrieve the lost energy. Without the rate, only one finger would be used at the receiver. The PN code renders the other fingers transparent. And combining such phasers, and what we basically have to do is, if I combine them as they are here, they would combine destructively, wouldn't they? Or if they get lined up like this, they end up constructively. And so, let me just show you. This is an operation, an example of the rate receiver. So assume that the 3 returns the fingers, each separated by 1 chip. Also assume that correlator number 1 is tuned to the code below, and correlator number 2 is tuned to a 1-chip delay from that, and correlator number 3 is a 2-chip delay from that. So here's a code, and by the way, I'm actually using a Barker sequence code, a pretty famous code, and that is 10111. Then again, 10111, 10111. That's a short Barker sequence. I'm just using that one as an example of a code. And here is the data. So, 10111 is then going to be multiplied by a positive going waveform. And the next 10111 is going to be multiplied by a negative going waveform, and then by a positive. So again, this is burying the signal within the noise, within the PN code. And that's what I get when I do that multiply. See, so I don't know if you can recognize that the middle part of this got turned around because it was multiplied by a negative going data stream. And the signal received by each correlator is the superposition of the delay signal copies. So here is delay number 1, which is 0 delay, and here is delay number 2, and here is delay number 3. This has 1 delay, this has 2 delays. So these are the same sequences with different delays, and this is after I have multiplied the code by the data, and then I add them up. This is the received signal seen by each correlator. Is just +1, minus and plus is 0, +1, +1, minus 1 is +1, and so forth. And each of those 3 correlators see exactly the same thing that you're looking at here. So now the receiver must learn the delays regularly, more frequently than the changes in multiplier. In other words, the receiver really has to have not just 3 receivers, but 4 receivers, because one of them now has to be a sounding device to say, where are those peak signal to noise ratios coming from? Where are those fingers? And so I'm assuming that the delay is always the same here, just to make our example simple, but the delay can change. And so so here you see the PN code with different delays used by the 3 correlators, and the correlation of the received signal with each correlator. So now I do the correlation and with the code, and then after I do that, I align, and this is the phase rotation. I push them back into line, and now I sum them together, and I basically get a very highly positive number representing a positive going pulse, negative number representing a negative pulse, and positive number representing a positive pulse. So that's the operation of the rate receiver. Let me just do. So this is one other example, and real quick, and that's the duration of the TDMA time slot should be less than the channel coherence time. So remember, the channel coherence time in a particular application, after all, if you're standing still, I got a certain channel if I'm standing still, and my channel says my coherence time is how big? It's infinite, because I'm not moving. And if I'm walking slowly, the coherence time is maybe hundreds of milliseconds. If I'm walking fast, it's, tens of milliseconds. But on a high-speed train, it's going to be pretty small, like a half a millisecond, something like that. And I want to make sure that I'm not sure yet. I have to tell you what the speed is of the high-speed train before I can tell you its coherence time. So, but I do want that whatever I call my time slot of TDMA, that represents some kind of a message bit or messages, should be smaller than the reliable amount of time I can depend upon. The T sub 0, which is the coherence time of the channel, is relatively the same over that amount of time. This assures that all the bits received in that stop time will be affected by the fading in about the same way. So, in a multi-bit channel, the same waveform received outside the category cell that are displaced by about half the wavelength is statistically uncorrelated. In other words, after a mobile system traverses a distance of half wavelength, it will typically experience a changed fading profile. The time that it takes to traverse in a moving system, to traverse a half wavelength, is going to be that coherence time, T sub 0. The GSM TDMA parameters were designed to allow for good performance in fading when traveling on a high-speed train. And let's take 300 kilometers per hour as a high-speed train and show that the TDMA slot time, which is has been designed to be exactly 0.577 milliseconds, is less than T0. Thus, each mid-amble, allowing synchronization, is a valid fading profile estimate. Okay. So this is the frame of GSM. The frame time is 4.6 milliseconds. There are 8 slots in the frame. One slot is about a half a millisecond, a little over a half a millisecond, 0.577 milliseconds. Notice there is a start and a stop. There's data, 57 bits here and 57 bits here, and there is a 26-bit training, and that is for synchronization. So notice, and here's the solution to it. We said, this is the sort of thing you might get on one of those certificate programs. If you're going to 300 kilometers per hour on this train, that's the same as 83.3 meters per second. At 900 megahertz, lambda, speed of light, divided by frequency, and we said that to try this frequency at 900 megahertz, this is 900 megahertz, is 0.33 meters. We said that the time it takes to transmit, to traverse that a half of that wavelength, and a half of that wavelength is 0.167 meters at the speed that train is going, is a coherence time. So you form this kind of a ratio. The speed that the train is going at 83.3 meters is to 1 second, as this half a wavelength amount of meters is to the time T sub 0. And you solve for T sub 0, and it comes out to be 2 milliseconds. And by the way, if you change 900 megahertz to 1800 megahertz, then the T sub 0 gets smaller by just the factor 2 here, 1 millisecond. So Well, train speed records currently are approaching 600 kilometers per hour, which would yield a channel correlation time of a factor 2 smaller than this, a half a millisecond if it were at 1800 megahertz. And as train's speed increased, at some point, and remember we said that 0.577, the slot time, has to be less than the coherence time. So if we ever get to the point where this is the coherence time, 0.577 is too big, and that would be a fast fading situation. So they'd have to make a change in the GSM TDMA system. Okay, we went through this very fast, and but I think that if I had anything to offer to you, I think I offered you a lot of pictures showing you characterization in a way that you can hopefully better relate to than simply looking at equations. And this is, for those of you who are going into the wireless area, this is a fundamental characterization of any wireless system. We always have fading. We always have multi-path. So I think it becomes a fundamental area for you to be good at and to be comfortable with, first of all. And I think you did. Remember, I was when I compared myself to my brilliant colleague, I always thought myself as wanting. There are lots of us in the world who are not brilliant. I'm in that category, and I find that seeing things pictorially and with lots of words will help you understand. And once you've got an intuitive sense of it, I think it'll help you predict the performance of systems easily and be very comfortable with evaluating systems. So thank you for your support, and I look forward to next time I'm here talking about OFDM. Thanks.
Any questions?
We're
good. We're good. So if no more questions, then we just end it today at this time. Okay, and then if you have any more questions, also send an email to me or send an email to Dr. Bernard Sklar directly.
Let me
excuse
me. Let me do this also. Right here. The notes are available online, and I just got used to using this Google URL shortlink, and I'm not sure it's working correctly. And in fact, can somebody right now, all you have to do is go to any internet. Can you get the internet from this room?
Yeah, we can get it.
Okay. See if you can get this set of slides by doing this. Just check it out. Without you having, maybe you have to be have a Google account. I'm not sure.
It brings me to the Dropbox.
Remember, you need the password. Here's the password when they ask for the password. My last name followed by IEEE. I have a medical thing going on with I won't be in a position. Can you send me your notes? No.
Okay, I'll send you those.
Send me those.
Okay. I can send you nursing.
It's a franchise, it's a big thing. I'll be very pleased to.
I can discuss this.
You can discuss it. I'd love to talk to you about it. Oh, no, it was, it's a terrible drive.
Oh, that's fine. Yeah, because you come making a big difference.
But you, give me a chance to look at your notes first.
Sure. The notes is different. I also have a lot of pictures. And I'm sorry that I have also a lot of equations that well,
That's okay.
pictures, equations, and tables.
Okay.
So really cheap and
I'll be glad to look at this.
okay.
Send me some.
Okay.
You have my email.
Yes. Okay. Then I don't have the fee.
No, I'll definitely get in touch with you.
Oh, okay. Because presentation is not,
Yeah, if I
the
can.
pieces, correlation is not as far as when you talk about it.
Yeah.
Yeah, I don't know if you can figure it out.
If I can, I will.
Yeah.